What if one of the most common words in physics has been misleading you this whole time? In this video, you'll discover what a boson really is, why it is not a tiny object moving through space, and how this idea explains light and forces. Before we begin, make sure to subscribe so you never miss more clear, informative videos like this. The word boson sounds like a thing, something small you could weigh or hold still long enough to study. It sounds like a building block, something the universe is made of, the way a wall is made of bricks. But that is the wrong kind of thing entirely. Think about when someone's phone rings. You don't see anything travel to your ear. What moves is a disturbance. Bosons are disturbances moving through something that already fills space, a quantum field. What physics calls a particle is just what the field does when it is disturbed in a specific way. This explains why light travels and why atoms stay together. They are expressions of the same underlying structure. At the center is spin, a fundamental property that appears when a field obeys both quantum mechanics and relativity. What exactly is being named when we call a photon a boson? If the word particle is misleading, what does that mean for our understanding of reality? The answer begins not with particles, but with something deeper, something that fills every point in space. Empty space is not empty. Every part of the universe, from the air around you to the space between galaxies, is filled with fields. Imagine a perfectly still lake. When you drop a stone, the ripples that spread outward are not new water. They are a pattern of motion. The water was already there. What changed was the condition of that water. Quantum fields behave in a similar way. A particle is not a tiny object. It is an excitation of a field, a localized disturbance like a ripple that carries energy. When you detect an electron, you are detecting the electron field in an excited state at that specific location. This changes everything. We are not living in a world of static objects, but a world of dynamic waves and patterns. These allowed patterns of excitation are what physics calls quantum numbers. An excitation of the electron field always has the same electric charge, mass, and spin. These are the identity of the excitation itself. They are not separate objects that happen to match. They are the same excitation mode appearing in the same field. Two manufactured objects always differ in small ways. Two electrons cannot differ in any way whatsoever. No difference exists. Among all these quantum numbers, one stands out, spin. It defines part of the structure of the excitation itself. Spin appears when we ask a specific question. What happens to a field excitation when you rotate the space used to describe it? Depending on how that description changes, we get two completely different categories of behavior in our universe. In quantum physics, some particles require two full 720-degree rotations to return to their original state. This strange behavior defines their spin. 9, 10 twice, 9, 10 twice. Particles with half-integer spin, like electrons, follow the Pauli exclusion principle. No two identical ones can occupy the same state at the same time. But bosons, the particles with integer spin, behave completely differently. For them, no such restriction exists. In fact, bosons lean towards sharing the same state. The more that gather together, the more likely another one is to join them, a behavior with no classical equivalent. This tendency to share is the foundation of Bose-Einstein statistics, explaining why bosons play such a unique and collective role in our universe. And this simple statistical behavior leads to consequences that scale far beyond individual particles. It shapes how light behaves, how matter can organize itself, and how entirely new states of matter can appear under the right conditions. To see how powerful that becomes, the next step is to look at what happens when many bosons are allowed to distribute freely across energy states. Imagine a simple setup. You have two identical particles and two possible states they can occupy. In a classical picture, you would expect them to spread out. You might think there is no reason for both to choose the same state over different ones. But bosons do not follow that intuition because they are truly indistinguishable and because their wave function remains unchanged under exchange. The way you count their possible arrangements changes completely. Instead of treating each particle as a separate entity, you count only the distinct configurations of occupation. And when you do that, something unusual appears. The arrangements where multiple bosons occupy the same state are not just allowed. They become statistically favored. This is not because of a force pulling them together. It is not because of energy minimization in the classical sense. It is a direct consequence of symmetry. This behavior is captured precisely by Bose-Einstein statistics. Developed in the early 20th century, this framework describes how identical integer spin excitations distribute themselves across available energy states. It replaces classical counting with a rule that reflects indistinguishability at a fundamental level. And when applied to real systems, it produces predictions that match observation exactly. One of the clearest examples is light. Consider a hot object like a flame or a glowing piece of metal. It emits radiation across a range of frequencies. Classical physics tried to describe how energy should be distributed across those frequencies, but it failed in a dramatic way. At high frequencies, the prediction broke down completely, suggesting that an object should emit infinite energy. This was known as the ultraviolet catastrophe, and it signaled a deep problem in the classical understanding of radiation. The resolution came from recognizing that light is made of bosons, photons, and that these photons follow Bose-Einstein statistics. Instead of treating them as distinguishable particles, the correct approach treats them as identical excitations of the electromagnetic field that can share the same state without restriction. When this is taken into account, the distribution of energy across frequencies matches reality perfectly. The spectrum of a flame, the glow of heated metal, even the radiation from the sun all follow this rule. The failure of classical physics was not about radiation itself. It was about applying the wrong kind of statistics to something that is not classical in nature. This means every photon that has ever reached your eye has been part of a distribution shaped by this principle. The color you see in every vibrant sunset, the warmth you feel from a glowing fire, and the light that carries information across space are all governed by the same statistical structure. But photons are not just examples of bosons behaving statistically. They reveal something deeper about what bosons do in the universe. The photon is the quantum of the electromagnetic field. It is what the field does when it transfers energy and momentum between charged particles. When two charged objects interact, something must carry that interaction across space. Classical physics describes this using fields, but it does not explain what is happening at a deeper level. Quantum field theory provides that answer. The electromagnetic field is not static. It is constantly fluctuating. Charged particles disturb the field around them, and those disturbances propagate outward. When another charged particle encounters that disturbance, momentum is transferred. The photon is the unit of that process. It is not always a visible particle of light. Often it appears as what physicists call a virtual excitation, a temporary disturbance that cannot be directly detected, but still produces measurable effects. These excitations are responsible for the forces we observe. When you bring two magnets close together and feel them push apart, nothing visible crosses the space between them. But the electromagnetic field is active in that region, and photons are the way that activity transfers momentum from one object to the other. Because the photon is a boson, it has properties that make this possible. It has integer spin, and more importantly, it has no mass. A massless boson can travel across space without losing energy over distance. This is why the electromagnetic force has infinite range. It can act across atoms, across rooms, and even across vast cosmic distances. This is not a coincidence. The range of a force is directly tied to the properties of the boson that carries it. A massless boson allows a force to extend indefinitely. A massive boson limits the range of the force it mediates. And this leads to a deeper understanding of what a boson is. It is not just a category of particle. It is the mechanism by which fields communicate interactions. Whenever two particles influence each other without direct contact, a boson is involved. It is the disturbance that moves through the field, carrying energy and momentum from one place to another. Every fundamental force works this way. The electromagnetic force is carried by photons. The strong force is carried by gluons. The weak force is carried by W and Z bosons. Each one is an excitation of a specific field, and each one has properties that determine how that force behaves. The strength, the range, and the nature of the interaction all follow from the properties of the boson involved. And once you see that, the idea of a boson shifts completely. It is no longer just a label for a particle. It becomes a description of how the universe transmits influence across space. But not all bosons behave the same way. Some are massless and travel freely across any distance. Others are massive and operate only at extremely short ranges. Understanding that difference is the next step in seeing how bosons shape the structure of reality itself. To understand how mass changes everything, consider something simple. A runner can cross a field quickly when carrying nothing. Add weight, and the effort increases. Add enough weight, and the runner cannot complete the distance at all. The range becomes limited by the energy required to carry that mass. Field excitations define our universe. Massless particles like photons can travel infinitely across space without restriction. But massive particles like W and Z bosons carry an energy cost that limits their reach, confining forces to tiny scales like the atomic nucleus. Then there is the Higgs boson. It stands apart, not carrying a force, but giving particles one of their most fundamental properties, mass. The Higgs field fills all of space. Even in its lowest state, it is always there, creating a resistance to motion that we perceive as mass. Some particles interact strongly with this field and gain mass, while others, like the photon, pass through it untouched and remains massless. From the light that travels across galaxies to the very mass that forms our bodies, these field ripples shape everything we know. At every level, the behavior of a boson follows from the structure of the field it belongs to, defining its role in the story of the universe. So the next time you hear the word boson, do not picture a tiny particle flying through empty space. Picture a disturbance moving through something that is always there, shaping everything you see, even when you cannot see it at all.